Hello, and welcome to this new video on our ongoing series of Mixtral versus LLaMA 2. As you know, Mixtral-8x7 is a very strong open source model from Mistral AI, and LLaMA 2 is another very strong open source LLM from Meta. So in this series, we are comparing them head to head on a number of points. In this particular case, I'd like to show you this YouTube page, which is from the TED channel, and it's focused on awesome nature. And you can find all sort of interesting trivia about nature, like why do animals form swarms, or the 3 different ways mammals give birth, and so on. So there's a bunch of videos here which are very interesting and contain all sort of nature surprises. So I thought I would put together a compelling exercise with this, which is let's extract summaries from all of these videos, and let's compare how these summaries are generated by the 2 different models we're considering, LLaMA 2 and Mixtral. I have created a repository with some notebooks. You can check it out on your own, but I think it's going to be more fun if I walk you through it. So let's go and let's dive right in. So here are my notebooks in my IDE of choice, which is VS Code. And this is connected to a VM in the cloud. And as you can see down here below. The VM I have here on the terminal, and I can check what I've got inside. And I've got 4 NVIDIA A100 80 gigabytes with PCIe connection. This is going to work just great. We don't necessarily need this many GPUs, but it's going to help with the latency. So let's go ahead and run this example in this configuration. If you need a refresher on how to create a VM or even how to connect your VS Code to a VM running in Hyperstack, please do check out the previous videos that we've got, and there will be links in the description. But picking up the case that we had in mind, which is creating transcripts for these YouTube videos, let's go first and extract those transcripts. And there's a handy Python library that we're going to use for that. First, initially, we're just going to perform a request, a classical HTTP request to fetch the source code from the YouTube page that we just saw. And there we extracted the URLs for each video from that page. And now we're going to extract the video transcripts. The magic happens inside this library, YouTube Transcript API, which, given the YouTube ID for each video, is going to extract the transcript. So as you can see, we're going one by one over all the videos in the list, extracting the transcripts. And we're done. Actually, that was pretty good. It took about 1 minute. This is just the magic in this library, which fetches the transcripts from YouTube. So we can go ahead and export those using pandas into a CSV file. And here you can see a table. Like for each video, we would have the video ID, which is what we use to fetch the transcript, the title, the transcript itself. So there you go. Meet Odontochelicemitaceae. For the first one, in tropical seas, flying fish leap out of the water, and so on, all the way up to 100 transcripts. And you can see more or less the size of these transcripts. So I think a summarization case is just gonna work out great because it's slightly too long. So we're gonna get them summarized with our LLMs. So that brings us to our next step. In our second step, we're going to get started by obtaining sample summaries with one of our LLMs. In this case, let's start with Mixtral. Before we do that, let me check what we've got here. And this is with the NVI top command, which we covered in previous videos. And here we can monitor in real time what is the memory and utilization of each of our GPUs. So we'll go back to this view in a minute. First, let's create our Mixtral LLM, and let's quickly go through the code here. We're going to be creating an object, a Python object, in which I keep the information about the model, like the tokenizer, the model itself, and we're leveraging the Hugging Face Transformers library behind the scenes to load all the elements that we need, and then we will use this library to perform the actual inference and manage the tokens and so on. You can inspect the details in the repository if you so would like. This took about 20 seconds to load into our GPUs. As you can tell, we're sharding the model. That means we're splitting the model in the 4 GPUs that we've got available. So it's gonna leave plenty of room for the inference requirements. Okay, back to our notebook. Let's continue by loading the transcripts that we obtained. In this case, because this is just a sample, we will just load the CSV file with 4 of them using the pandas library. And let's inspect what the prompt is going to look like. Before we do that, let's go to the prompt template over here. There. So this is our prompt template. It's going to say the following is a transcript from an educational video in Nature. Summarize the transcript, extracted the main takeaways, focus on curious facts, use a friendly tone, and write in simple English. This is going to be the video title, the video transcript, and then we will ask the model to summarize it with summarization of the video transcript in 100 words or less. We are using, in this case, the LLM, the instruction fine-tuned versions of these LLMs. So this is going to be the LLaMA2-70b chat variation and the Mixtral-8x7 instruct, because these are models which are capable of following instructions. They're going to be just fine by following this prompt. So back to our notebook. Let's see what an actual prompt is going to look like. You saw the part belonging to the template, and now we substituted the title and the actual video transcript that we would like to summarize. This is looking fine. So let's summarize a few, well, just one. Let's summarize just one, just to see how that goes. We can go back to the terminal representation, and we see our GPUs working away at the inference. And you can see that all of them are working because we have sharded the model, we have split the model among 4 GPUs. The first thing that we can notice is that, well, they're working, but they're only working up to 10% or so. So it doesn't look like we're making the best use of our GPUs. And we will get back to that later in this video. For now, we're done, and we created those summaries, or that one summary, and let's look what that looks like. This video explains how turtle shells evolve twice. The first turtle ancestor, the second turtle ancestor, the first fossil. Okay, looks pretty solid to me. Modern turtle shells are diverse. And we saw here that it also extracted some curious facts, as we just asked in the prompt, remember? And it goes like turtles who have 2 shells that develop separately, the upper part of the turtle shells, called the carapace, the bottom half of the shell, the oldest known turtle ancestor, and so on. So it looks like a pretty comprehensive summary. Let's examine the same example now with LLaMA 2. It's going to be just the same, just to make sure that our script is working. And we can see our GPUs being occupied with the model weights. Okay, the model was now loaded onto the GPUs. Let's load the pandas data frame and let's get the summaries. In this case, just one summary. Similarly to what we saw with the Mixtral example, we see the GPUs working away, but with limited utilization. Here we're using more memory and more computation because LLaMA2-70b is a larger model. And here what it looks like. The video discusses the evolution of turtle shells, which have two separate shells that develop independently while the turtle is still an embryo. The upper shell, the lower shell. The shell provides protection for turtles, and similar to what Mixtral did, it extracted some curious facts. Like turtles have two separate shells, the upper shell, the lower shell. So in principle, it also looks really comprehensive, more or less similar to the one we got with Mixtral. As you can see, these two models look pretty capable of producing the kind of summaries that we need for our experiment. But you saw that we didn't make a great utilization of our GPU. So let's explore that in more detail. In this part of the code, we are leveraging the transformers library from Hugging Face to perform some inference. So we basically take the tokenizer and we load the model into the GPUs. And the key part here is these two parameters. Device map will make sure that the model is split among the available GPUs, as you just saw before. And attention implementation for flash attention 2 is going to make sure that we use a very efficient implementation of the attention mechanism running on the GPU for great acceleration. In particular, what this implementation does, it performs fused operations to reduce the access of memory. So it is very efficient to run it on the GPU. This is already great, but as you saw, it wasn't quite enough to produce a great utilization of our GPU. But here is something else we can try. Without getting overly technical, let's just go very broadly over the code here, which is we're going to iterate over all the summaries in batches. And each batch size is going to be a parameter that we can decide. That means that we can perform the inference requests either 1 by 1, 2 by 2, 4 by 4, and so on. So I have prepared some script over here actually to perform a systematic study of that inference with different batch sizes for both of the models, both for Mixtral and LLaMA2. We're going to try and perform those inferences to obtain the summaries with different batch sizes, 1, 2, 4, and so on, all the way up to 100. So I'm going to go to the console and run that, and I'll get back to you when it's done. Our experiments are now done, and we have collected all the outputs in this folder. So you can see that for each of the models, we collected a file for each of the different experiments. So in this one, for instance, you see that the underscore here represents the batch size. So we performed summaries 1 by 1. That means that we sent an individual request to the LLM for each of the transcripts. If we go to batch size 4, then you can see that we packed 4 summaries into a single request. And this does a greater utilization of the GPU by putting more load onto the system while processing in parallel. I have put together this notebook to go over the results of the batching experiment in more detail. So for each of the output files, you will see that here at the bottom there is a summary which collects the number of summaries that were generated, the average number of tokens per second, the time it took for the experiment, and the batch size. And this is present for all the output files over here. So that lets me go to the notebook and collect all those tokens per second in a pandas data frame, both for Mixtral and LLaMA. And for easier view, let's plot it. This is quite an interesting chart. The first thing we notice is that as we increase the batch size on the x-axis, we get significantly higher tokens per second. So that's already giving you a great indicator that batching is the way to go to achieve better GPU utilization. Basically, you're just getting more tokens on the same amount of time. The second thing we notice is that Mixtral is faster than LLaMA 2 for small batch sizes, but for larger batch sizes, efficiencies start to fall on the side of LLaMA 2, which achieves more tokens per second. And there is another view down here, which I wanted to share with you, which is the speed up. Let's plot it as well. The blue line is the ideal, which means that for 32 batch size, we would ideally be 32 times as fast. And for 64 batch size, we would be 64 times as fast. In reality, there are effects that reduce that ideal speed up. But what's interesting to notice here is that the green line over here, which belongs to LLaMA, is higher than the orange line belonging to Mixtral, which again comes to say the same conclusion that we reached above, but plotted in a different way, which is that the efficiencies for greater batch sizes work better for LLaMA than for Mixtral, which allow us to obtain the highest number of tokens per second for LLaMA2-70b. Remember, this is for a vanilla implementation of our inference request by using the transformer library from Hugging Face, just by sharding the model onto the GPUs and using the flash attention to implementation. So looking at these results, we might be tempted to ask, okay, since we need to generate 100 summaries, and we can tell that by batching more requests together, we get faster inference, why don't we just pack all 100 summaries all at once, since they are independent? It turns out it's not quite as simple. And if we evaluate the output of the experiment of running the 100 summaries all at once, we find out that we run out of memory. So the more requests we perform, the more the demands are exerted on the memory requirements for the GPU. So even though we're using 4 GPUs of 80 gigabytes each, we can definitely run out of memory if we pack too many requests at once. And the same happened with the smaller model Mixtral. This is too much of a requirement, and the execution is aborted. As you can tell here, we are a little bit closer to the requirement of Mixtral than to the requirement of LLaMA 2. But in either case, we can't pack all that many inferences all at once. Let's wrap up by going over the main conclusion of this session, which is that you can batch inference requests for better GPU utilization and higher tokens per second. In the next episode of our ongoing series of LLaMA 2 versus Mixtral, we will have a look at the actual summaries generated and how well they rank in terms of quality. Hope to see you in that new session. Until then, stay safe. Thanks for watching.